have a bit of an agenda so we can all know what's coming. I'm just going to go through some of the topics today, and the first one we're going to take a look at is what serverless can do for your team. And this is kind of an intro to serverless in a way that you as a team lead may want to know. Maybe you've considered serverless and are thinking about using it in your organization, or you're already convinced, but maybe you would like some talking points to share with others in the team. Then we're going to take a look at what the structure of a serverless project can look like, and what are the best ways to kind of put things together when you're building a serverless project. And then hand over to looking at a generalized sort of software development lifecycle of building a serverless application. And then from that, going a bit more into detail about what it looks like from individual contributor in your team's point of view, how you go on a day-to-day basis building, a serverless application. And then we're going to get into the sticky topic of how to test locally, or why you might not want to. And then finishing it off with looking at managing shared and production environments, which can be a tricky thing to do once you've got your application built and you need to put it into production. How do you manage that from there? How does that look? All right, so let's dive right in and take a look at what serverless can do. And I just wanted to set a context as well as what do we mean by serverless? What is, there's many definitions out there about what serverless really means. So in a very simple definition, a serverless application is composed of serverless services, which seems kind of tautologous. But serverless services, if we define that further, are essentially services available to you in the cloud that you can consume that are fully managed by the cloud vendor. So unlike services like EC2, RDS, Elasticsearch, for example, these serverless services are fully managed by the cloud vendor. You pretty much don't have to configure or worry about load or anything like that. You can just straight up consume them and use them. And what makes them great is that, as mentioned, you don't have to worry about capacity. You don't have to worry about whether one CPU is going to be enough to handle a specific number of users. You just consume the service, and all the capacity management and load balancing is managed for you. These services also have known limits, and they're actually written in, whereas other services just have a cluster with a specific size, and you kind of hope that you're going to meet the limits are going to be within what you need. Serverless services tend to have limits that you can code against, and they have an API attached to them that also include those limits. So what's great about that is if you're consuming these services through an API and you hit limits, you're going to get sane responses back that you can then code against and have safety against. And the TLDR, the quick way just to kind of see if you're working with a serverless service or not, is if this service that you're looking to consume happens to want you to set a cluster size or capacity, it's probably not a serverless service in that case. If it's worried about CPU and memory, you're probably not using a serverless service. So throughout the webinar today, I'm going to drop a couple of tips here and there, which are just things you can take immediately and kind of make use of. And the first one I want to mention is when you're building a serverless application, you should try to prefer these serverless services to use when you're building your application. It just helps make things easier, as you'll see as we continue in various ways. Now, the advantages that serverless gives you, apart from what I've mentioned in the definition, is that serverless allows you to do things like have your time to MVP be drastically reduced. If you're in a greenfield state and you're building something brand spanking new that you still need to prove, you often want a very quick MVP just to get that out there, see if it gains traction. And serverless really allows you to do that very easily. But it also allows you to look at use cases in your existing application. So you can very quickly iterate on new stuff that you want to try out without having to spend a lot of time and effort. Serverless lets you get stuff out pretty quickly for that as well in your existing applications. If you're looking to modernize your existing systems and make them more asynchronous and distributed, well, that's kind of bread and butter for serverless applications. They tend to work really well in asynchronous environments, and because you're using multiple services, they're kind of going to be distributed to begin with. One of the bigger advantages you get out of building serverless applications is you're not waiting for infrastructure to be provisioned. You haven't built this brand new feature and now need to throw it over the wall at the DevOps team and say to them, put this somewhere, make space for it, make sure it's provisioned. You are integrated into the entire process of building the solution and putting it out for your users to eventually use. And one of the big advantages is that it kind of reduces overhead. There's a lot to talk about here because server-based architectures that we traditionally used to have infrastructure up and available 24/7, and these infrastructure elements consume resources and cost you per hour, whether they're actually being used or not. And we're talking about virtual machines and relational database type systems where there has to be an instance of some kind up and running, and you're getting billed by the hour for these. So the advantage that serverless services give you is that they're billed by usage. And when it comes to 2 a.m. in the morning and you haven't got anybody on your site or using your application, you're no longer being billed anything. API Gateway bills for the number of requests that are made. And if there's no requests currently being made, you're essentially not paying for anything at that point. Yet it's still going to be permanently available in case those requests do start coming in. And the other side of this is that total cost of ownership isn't just the AWS bill, because you'll always find somewhere on the internet somebody's going to present a server-based architecture and a serverless architecture running similar applications, and they may show that the server-based architecture in the AWS bill is cheaper. Unfortunately, total cost of ownership when it comes to that isn't quite as simple, because when you come to a server-based architecture, you do need manpower in order to keep that up and running. And the more traffic you generate on this server-based architecture, the more of that manpower you're going to need to continue to keep it up and running, maintain it, and load balance. And I decided to take a little bit of a deeper look into this, just a nice example for the webinar today. And I ended up just doing a quick little Google search of the average salary for a DevOps engineer in the US. I just literally typed that into Google, and this was the result. And while this is an average, so some people might be earning less, some will be earning more. Different regions in the US will have different brackets. We can just take this as a generally good number to take a look at. So I decided, if I'm going to be paying this for a DevOps engineer to keep my server-based infrastructure up and running, what does that equate to in serverless infrastructure? So one of the most notoriously expensive resources or services that you use when you're building a serverless application is API Gateway. And in API Gateway, API Gateway V1 or REST APIs is the most expensive version of API Gateway as well. So let's take a look at that. Let's use that as our comparison. And as you can see, this is the calculator on the API Gateway product page. And I've decided to take a look at what 3 billion HTTP requests per month is going to cost me. And while I can also set a cache memory size of 237 gigs. That's the maximum cache memory available on API Gateway, so let's max that out. And I've got 3 billion requests per month here. And if you're an organization running an application with 3 billion requests per month, that's not insignificant. That is a fairly large number of requests. And when you look at the calculation, you can see per month, this is going to cost me about $10,500 a month. Multiply that by 12, and that's just slightly over the annual cost of a DevOps engineer. And at this point, if you're running at 3 billion requests per month, you've probably got 1 or 2 DevOps engineers on your team already to help you manage the load from these HTTP requests coming in. But ultimately, you can see that it's not just a case of comparing AWS bills to see how more expensive your serverless infrastructure might be. And the other side of this is that serverless applications tend to be more forgiving when you're deploying things as a developer, because managed services and even Lambda are incredibly well isolated from each other. So in a server-based infrastructure, if you've got slightly inefficient, if you've got multiple threads running on a CPU on a server, you can often have situations where those threads end up affecting each other. Some threads start consuming more CPU than they should, and others will suffer for it. And this results in a bad user experience. And if your code is slightly inefficient in a serverless world, you might not even notice this. Tests have shown that even with Lambda functions, running thousands of Lambda functions simultaneously, the effect of noisy neighbor issues is massively reduced when it comes to Lambda. So even if you happen to deploy code into production that's slightly inefficient, you may not even notice it. And then when you look at the extreme example where you have incredibly inefficient code, traditionally on a server-based infrastructure, this could bring an entire application down. This could bring down an entire cluster where you suddenly have virtual machines trying to spin up, trying to be added to a load balancer, trying to provide additional infrastructure to manage the sudden load increase after deploying some inefficient code. But in the Lambda world, this ultimately would not bring your application down. Your Lambda functions may have higher latencies, and then you'll be able to look at that and potentially correct that. And we'll take a look at that in a second, in a few minutes. But this is the biggest advantage you get. It's very forgiving, which is why you often get the advice in the serverless world that when you're building something, get it working now and optimize later. You don't have to spend as much time optimizing for your infrastructure as you do in a server-based infrastructure as you do with serverless. And that's a really great advantage. All right, so we've kind of taken a look and gotten some context there. If you need to sell serverless to somebody, you've got a bit more to talk about, some more things to point out to them. But if you now started building a serverless application, or you're about to and plan to, how do you structure a serverless project? And all the steps we're going to be talking about today, if you're right in the trenches right now, busy building your serverless application, and things aren't, and what you're currently doing isn't matching with what we're presenting today, all power to you. If you find what you're doing is working, keep at it. This doesn't dictate that you should be completely ripping things out the way you've got them now and trying to change everything. Rather stick with what works for you. But if you are greenfield or looking to get started, well, this will probably be a good model to follow. So what we find when building serverless applications is that using a microservices pattern is often the recommended pattern. And as an example, this is the structure of an application that I've worked on over the past couple of years. And you can see this is a collection of microservices for the application. We've got an authentication services that's going to manage user details and logging the user in. We have a messaging service that will send emails and SMSs and even in-app messages to users. A checkout service for managing credit card payments and so on. But when we talk about microservices, we also don't necessarily mean the exact definition of microservices as you might find in publications on the web. I've got the micro in brackets because while you can go full on microservices, microservices might be too fine-grained. You can go a little bit more, have a bit of a larger scope when you're looking to define what your services look like. So traditionally, the reason why microservices was the recommended pattern with serverless was because of a genuine logistical limitation that was in place for developers, where CloudFormation was used as a way to maintain state of your stack, and CloudFormation used to have a limit of 200, which was kind of low but workable. And microservices were recommended to help you keep below that 200 limit. This has now since been increased to 500, which is great, thanks to AWS. But you might still reach this 500 limit. So generally speaking, using microservices pattern is also a good way to keep you below this. It's not as big of an issue anymore, but it's a good thing to bear in mind. But there are other reasons as well. Because you're building a serverless application, which, as I said before, is a collection of serverless services that you're busy using, it may end up being very complex, having all of what would have been your microservices bundled into a single monolithic application with all of these distributed systems that you might be using inside AWS. And this complexity starts becoming difficult to manage, and potentially when you're going through processes of onboarding new developers to your team, they may look at the monolithic code base and start struggling to figure out where all the boundaries lie and how things operate together. Whereas if I, for example, as a new member of the team, need to go work on my authentication service, I can grab just that service, go look at exactly all the interactions and functions that I'm working on, and know exactly how the authentication service works. And the only reason I care about any of the services is the communication boundaries between them. I don't need to be deep into the code for all these other services just to fix something wrong with the authentication system, which is kind of useful. It also, especially as you grow your team and you start getting more members on the team, you might end up breaking up into multiple teams. And microservices is a great way of allowing teams to take ownership of their individual services, where you might have one team has 10 services to their name, another team has 6, another team has 15, whatever it might be. Those teams can now focus on just the services that matter to them, to maintaining their part of the application without being swamped with the monolithic application that contains all of these things together. It also means that they also don't need to worry about other teams and their services beyond the communication boundaries, which helps simplify things, especially in larger teams. And if you're wondering, how do you define what these services look like, where the boundaries lie, domain-driven design is a really good tool for this. And I'm not going to go into a lot of detail talking about domain-driven design. It's a huge topic, but it is a great tool that you can use to help quantify and break up what your application would look like in a microservices environment. So I highly recommend that. And I'll kind of briefly mention this, but if you're going to build microservices, you need some way to have communication between these services. And what we found really useful is using inter-service communication, asynchronous communication methods between services. The tricky bit is if you start using synchronous communication methods like HTTP requests or direct Lambda invocations, those can work. However, they suffer from having issues when there are errors. So if your synchronous request fails, what then? How do you make sure that the request actually completes at some point? Whereas the asynchronous communication methods using tools like EventBridge, SNS, SQS in AWS, for example, have great fallback mechanisms, automatic retry mechanisms, and ways for you to help fix a problem if a problem occurs. Whereas synchronous communications generally don't. So that's where I've got tip number 2 is right now you can start applying this to your application immediately, is to perhaps focus on using asynchronous communications more when you're trying to do inter-service communications. And I've actually found asynchronous communication methods useful within the same service, but chatting between components within the same service. It can be incredibly useful for all of those fallback mechanisms. The other part about structuring an application is how do you manage version control? And version control, thankfully, isn't a massive architectural concern, but it is an organizational concern, and you might need to consider how you construct things in your version control systems to help maintain control over things. So the starting point here is to consider doing a repo per service. So you have all those services I listed before, and each of those could be in their own GitHub repo. However, this does become tricky to manage over time, especially as things grow. And it doesn't help with your team potentially not seeing the context of all services together. Also, as your quantity of services grows, it becomes difficult then to manage deploying these services into multiple environments if they're in separate repositories. So the next step up from that is to consider using a single repo for all the services together. And this is useful. So again, if you have somebody new join your team, they can do a single clone out of your repo, and they now have all the services available to them to explore as they need to. And if you need to deploy all these services into another environment, there are ways to do this with scripts and so on that can automatically deploy these services out into an AWS account, which we'll talk a bit more about AWS accounts in a bit. And then the step above that, and the single repo for all services is great until you get to the size where you need multiple teams and breaking your application apart more coarsely. The tricky bit there is that, you're going to have a single repo with all the services and could be swamped with all the details. So at that point, you're going to start looking at building multiple repos with multiple services. And this is to help break apart, create a separation based on your team distribution, or an even coarser boundary on your feature set for your application. So putting together the structure of the application is a relatively simple concept to get around. But let's take a look at what sort of the general software development lifecycle looks like when you're building a serverless application. And I'm going to take a kind of very top-down view here, sort of broadly looking at the process that a developer might go through going from starting a brand new service that needs to be added to the application to getting that out into production, and what that whole sort of flow looks like. Obviously, this is going to start with someone on the team creating this brand new service, using the serverless command to use a template, or perhaps an existing template that the organization uses internally. And then we initially, when you've got this initial setup done, you're going to deploy this initial setup into the developer's development environment, into their AWS account. And from there now, as a developer, I can go and start building my solution. I can start adding my business logic and writing my code, setting up all the additional services that I'm going to need to interact with this new service I'm building. And then when I'm ready, when I've got to the point where I want to actually test something to try it out, I'm going to deploy this into AWS to do some testing with this. And this is the iterative process where I'm going to end up going back to editing code locally. I've seen that I've got errors thrown in my CloudWatch logs for some reason, or my logic just doesn't seem to be doing what I expect it to be doing. So I'm going to go back and keep editing my code and deploy to AWS, and keep editing and deploying in this way to help me get to a working version of my service that I'm building. And I've gotten to the point, I'm happy. I think this is all I need. It meets the spec. I've done what needs to be done at this point. I'm a happy developer. Now I want to deploy this into a shared environment because I want to start looking at integrating this into the work the rest of my team has been doing potentially, and how this looks for the other services that we're going to be deploying into as well. So there's a shared environment here that I can use to deploy my service into, see how this all works. And if I notice that there's a problem, I might need to make some corrections, and that's why I can come back to this process again where I'm going to be testing. Once I'm happy in the shared environment that things are working the way that they should, after doing my integration, testing, and correction, I'm going to then create a PR for review by the rest of the team. And then there's going to be some feedback from this. And then, of course, if there's feedback that requires me to make changes to my code, I'm going to go back to the process of editing locally and testing, and then forward again to where I'm editing my review or my PR or creating a new one. And once we've got the solution reviewed by the team and everybody's happy with what this looks like, ultimately my pull request is going to be merged into my shared development environment and then deployed into the shared development environment for us to do a last bit of sane checking that everything is working as it should, test against the other services and so on. And then ultimately it's going to get merged into the production branch to deploy that into production for all the customers and users to see. One of the things you may have noticed here looking at this entire process is that nowhere around here have I ever stopped to say, oh, now we need to wait for the end of the sprint, or we're going to wait for a specific version to be released, or it's going to be scheduled for deployment at some point in the future. The entire process is a developer taking the service that they're building, working on it until they're happy, until the integration tests are happy, until the rest of the team is happy potentially, and then it's going into production. This flow just sort of continues. And that's where another tip comes along, is that what we found is that with serverless development, continuous deployment works incredibly well. Because we are in the process of building a solution that goes from code into AWS, into AWS for integration testing, into AWS for final thumbs up from the team, into AWS for a final staging environment. We've essentially been replicating the production environment throughout this entire process. So we can far more confidently know what to expect when it goes into production, because things are very close to production in this case. So continuous deployment works really well with serverless development, and especially in this kind of workflow. Of course, if you're still a bit leery about just letting developers deploy things into production, even after review by teams, there are mitigation strategies you can use, things like canary deployments, which there are plugins for the serverless framework, for example, that allow you to attach canary deployments to your deployment process, which will authorize 10% of traffic to go to the new code that's been pushed out, and progressively increase it over time, or roll back if there's errors. These kinds of things exist. But ultimately, continuous deployment is a really great mechanism to use. So let's break that down a bit further. We've kind of looked at that general flow, but let's look what the actual day-to-day of the individual developer looks like. And for this, I want to just cover a couple of things to consider how this environment for individual developer is kind of really different to how we've done it traditionally in the sort of server-based architectures and projects we've built. So the most obvious one is that we're dealing with cloud-hosted managed services as primitives. When you're building a server-based architecture, what you're working with is something that's going to execute on a CPU with a certain amount of memory and possibly have some traffic on the same machine, potentially working together. That's not the case when you're building a serverless application. You're using a Lambda function, you're using API gateway, you're not necessarily talking directly or concerning yourself directly with a machine that has CPU and memory. You're concerned about a managed service with specific limitations. We're also trying to build our solution using serverless technologies, which gives us a lot of advantages in that deploying these out don't cost us anything if we're not actually using them. So development cycles become really cheap. And one of the big advantages is tools like the serverless framework allows us to redeploy the service that we're building reliably and precisely. So I can take the configuration I've got and deploy that into my AWS account, then deploy that into a staging AWS account, and it's going to be the exact same thing, and then do the same thing into production. So all along the way, I've got this precise, exact deployment that I'm doing on all of these environments, and I can be confident that what I'm deploying locally is what's going to end up going into production right at the end. This means that along the way, we're now in a situation where we are able to actually test what we're building against an exact replica of the production environment, which is a rare thing to be able to do as a developer. So I'm just going to go through a bit of a demo. I've put together here a video to kind of show what this process might look like from a developer's point of view. And this takes us right to where we're starting and building a new service. So as a developer, I'm now in my terminal, and I've got the serverless framework installed, for example, and I'm going to use the serverless command to start a new project. And I chose an existing template there to start my new project, but I could have used the serverless create command to rather choose a template that we've designed internally if you want. I'm going to name my project now, and now it's just pulling out the template and giving me the starter code. We're then going to get prompted about connecting, logging in or registering to the serverless dashboard. In this example, I'm going to say no at this point, but we are going to talk about the serverless dashboard in a bit more detail later. So if I say no here, it's then going to ask me if I want to deploy immediately. And remember, part of the flow was that we do want to deploy something into AWS as soon as possible. So we're going to say yes in this case. And it's then going to go ahead and use my local AWS credentials sitting on my local machine to deploy into my own AWS account. And this is going to use the regular deployment process that you find with the serverless framework and put that into my AWS account for me to start working on and deploying to and testing with. So now I'm going to open up my IDE. I'm going to cd into the folder first and open up my IDE. Let's take a look at some of this code. And you can see it's a very simple service. The serverless.yaml is not very complex at all. It's just a little demo application for the purposes of the talk. But in my handler.js, let's go make some changes. So I'm just going to update my return value here so that I can just see I've actually made a change. Let's drop a console log so I can store some logs in CloudWatch here. Just a regular old console log, a bit of a typo. Let's fix ourselves up. There we go. We've got some stuff changed. And let's save the file. I mean, we're going to drop back to the IDE, and we're going to use the deploy function command. Now, this is a really great command to use to help get code I've just written out into AWS as fast as possible, serverless deploy function. And what this feature does is it literally just takes the code I've written, only the code changes, and pushes that out and changes that in Lambda directly. It doesn't invoke the full deployment process using CloudFormation that you might get using serverless deploy. And what this means is that it'll literally take me seconds to deploy my function out into AWS. And there we go. My code is now in AWS. So let's run an invoke here, and I'm going to remotely invoke my Lambda function directly in AWS so that we can test this. And immediately you can see I've got a result here. There's my status code from AWS. I have made a change, the change that we made. But let's take this a step further now. If I'm going to be developing an application and deploying and testing directly in the cloud, I need some way to look at my logs. So I'm going to open up another pane here, and you can see on the right, I have a function, a command list, serverless logs-f hello-t, and this essentially lets me stream into the logs generated when my Lambda function is invoked, and I'm tailing those logs as well, so I'm automatically going to get some details about that. So let's run the invoke command one more time. I'm going to invoke my function, my hello function, and we should be getting the response from our request, and there is the status code 200 and the I have made a change. And then in a few seconds on the right, I'm going to get my log from CloudWatch printed as well so that I can see the console log that I put in. There we go. Let me log something here. So now as a developer, I'm going to continue, and there we go back to my IDE. And let's make some changes here. So I'm going to change my message to another change. And let's go back to the terminal, and let's redeploy this using the serverless deploy function command. I can just use -f, doesn't have to be deploy function, and it still does the same thing. And in a couple of seconds, my code changes have now been pushed. And now I can invoke again. And once I get my request back, I can see I have made another change. So there's the changes that I've made. And in a few seconds, I'm also going to see my logs right next to them. These were all real-time things. There's nothing cut here or sped up. And that's kind of the process that you can look at going through as an individual developer working with deploying into AWS, getting logs out so that you can rapidly iterate on the code that you're writing. If you run serverless deploy and you made infrastructure changes, so you've added a DynamoDB table, that might take a little bit longer. But once you've settled down on the infrastructure you're going to use, most of your work is going to involve making changes to code, and you can very rapidly go back and forth on that. All right.
Hey, Gareth, before we move forward, we do have some questions rolling in. I want to take a pause here for just 1 second to answer some of these. It'd be great.
Sure, let's do that.
Ryan Token asks, as a third-party service, being cloud agnostic is a serious draw. We built a lot of our SLS application on AWS. It seems like the other major cloud providers don't have nearly the number of serverless services that AWS does. Can you discuss the difficulty of moving between clouds from SLS?
So it is, unfortunately, multi-cloud services are rather tricky to do. The biggest reason is that any application that you're looking to work across multiple, or any framework that you want to use across different boundaries, the problem is that any framework that you want to use on that is going to have to reduce itself to the lowest common denominator. Which makes life a little difficult because there are really great features out of all these services that are available to you in the cloud vendors. And if you start trying to support DynamoDB and Cosmos DB and Firebase or whatever the equivalent is, I've forgotten the name now in GCP, the problem there is that they all don't have the same features, and all you're going to be able to do is provide what all of them provided at the base level, which isn't great. And the architectural principles between them can sometimes differ as well. So that gets tricky now because now you ultimately have to change architecturally how these services are built, which kind of removes the whole point of being cloud agnostic. So that becomes a very tricky thing to do. One technique that we've seen folks use when it comes to doing things cloud agnostic is if there are specific services that they want to make sure are cloud agnostic, things like databases, for example, tools that are specifically designed for infrastructure as code tools or configuration tools like Terraform and so on that have pretty good cloud agnostic capabilities, because that's a very good part of what they focus on. A lot of these shared services could eventually be set up that way, and that's probably one way to look at doing that. But it's a very tricky situation to work with serverless. The only reason I'm taking a bit of time on this question is it's a relatively big topic. So the other way to help you with this is when you're building your Lambda functions, for example, if you want to have your code as agnostic as possible, we have seen organizations who essentially built wrappers around their Lambda functions. So all their business logic is abstracted out into object-oriented structures, usually using specific classes and so on. And the wrappers for AWS Lambda versus Azure Functions versus whatever else, it will then be used in those environments and will talk to the same business logic in those classes, but the specific wrappers for the cloud vendors would be used in that case to help just sort of translate between those different environments. But yeah, hope that helps.
We also have a question from Andrea. Let's say I'm a single developer making a serverless application that might grow and give me the possibility to hire other developers. What would be your approach, spending more time now or thinking later on it? It will be difficult in the second case.
All right, so that's another advantage potentially that following a microservices approach right at the get-go gives you. The example that I gave with going out was an application that I started by myself as a single developer, and that was eventually taken over by a team of about 4, I think, whatever it was. And the advantage there was that breaking it up into multiple microservices means that you've already got things separated out if you want to have somebody take control of some part of it and you maintain another part of it, or multiple members of the team and so on. So using that microservices architecture for the structure of the application is a really great way to get started with that. And ultimately, if you don't hire anybody and it's just you forever, fine. I mean, the microservices structure still works incredibly well, even as a sole developer. So.
We also have a question from Joanna. Is it better to have a single or mono repo?
So ultimately, it depends. In a lot of cases, I would tend to suggest that a single repo for all your services is a good way to go. And ultimately, if you grow really large, then you might have multiple repos, each with multiple services, but that'll be based on your team structure as opposed to necessarily the application structure, because you'll have teams using a specific repo, another team using a different repo, and the services they need within them there. So yeah, a single repo for all your services together is usually a very sane approach.
And we have a question from Juan. Does Knative also apply with the definition and services practices of serverless in this talk? For example, serverless is fully managed by vendors.
So Knative is a unique situation because Knative isn't necessarily in a place where you can just, as a sole developer with limited knowledge about infrastructure, just go out and start building things with Knative. You still need a fair amount of sort of backing on understanding what Kubernetes is, what Docker is, kind of how those things work together, just so you can optimize things better. It doesn't completely abstract away all the stuff you need to know when it comes to managing containers and clusters and so on. The problem with Knative as well is that you're going to be building services, like maybe you need a message queue system. Are you going to then use SQS, or are you going to use Knative to spin up your message queue system in that way? And so you start moving away. You start moving away from being serverless, and you're managing more of that stuff yourself. What about receiving HTTP requests? Are you going to spin something up in Knative to manage that, or are you going to use API Gateway? And if you're doing Knative, again, you need to know about Kubernetes and Docker containers, all those kinds of things. And that starts making that more complex to manage. One of the sort of guiding principles that I feel when building serverless applications is to choose the option that keeps things simplified, and using the existing managed services that you don't need to configure and set up in a tool like Knative, for example, is far simpler over time, and means that your management, the level of management that you need to apply to your application is much lower, and generally that ends up being, in the serverless world, a better long-term bet. How that fits with the organization and what the skills in the organization are like, that's another topic entirely. So that's why I was saying it's very difficult to have a single exact method that works for every case out of the gate. So hope that helps.
Yeah, these are great questions, guys. We got two more. Ryan Token asks, why is there no serverless plan command similar to Terraform's Terraform plan that lets you preview all the changes you're about to make upon deploy?
All right. This is a tricky question. The closest we've got is the serverless print command, and this is a way for you to get a version of your serverless.yaml file printed out with all of the variables replaced with the actual literal values. So you can see that $SLS stage or $param value that you put in, what that's going to equate to when you're actually doing a deployment. But one of the reasons why serverless plan is a little bit tricky is because the command for a serverless deploy is meant to be relatively atomic, and is not designed to only describe the changes that are going to be made. Because with CloudFormation and the fact that you can deploy to multiple environments very easily with the serverless framework, we don't have to have a CloudFormation stack existing in your AWS account for you to make a deployment. So there might not be a stack, there might be a stack. We don't know this ahead of time. So we create a CloudFormation configuration that we send to your AWS account at every deploy. It's completely modular and on its own. It doesn't depend on an existing stack. And that gets sent to CloudFormation, and CloudFormation works out the differences after that. There are plugins you can use that allow you to do something similar to a serverless plan, and that will essentially do the deployment but interrupt the deployment part and get CloudFormation to do essentially a diff on your CloudFormation stack. And I can't remember offhand what that is, but feel free to send me a message afterwards and I can look that up for you and maybe send you more details on that.
And we also have a question from MJ. Do you recommend testing from the cloud instead of local testing? Like with SAM, there's SAM local that allows developers to test locally. Is there equivalent tool for serverless framework?
All right, so I'm going to say we're going to talk about that shortly. So
all right, I'll resume.
All right. So continuing, we've taken a look at what it looks like for an individual developer to go through sort of that workflow and iterate over their code and deploy into AWS. But let's just take a quick look at what the development setup would look like. So in the best case, what you've got is a situation where each developer on your team has their own AWS account. And this might sound a little extreme, but we'll also cover that in a second. But the reason for this is that this gives them the freedom to not be scared of testing and trying things out and experimenting, which can be incredibly helpful when you're building serverless applications. When you're combining all these things together, you want to see that it works without potentially overriding what someone else on your team has done. And this also means that that developer can now take the other services that work together with the one they're building and deploy them together into an AWS account to work out the interactions between them. It just helps us get closer to that, as close to production as possible. And remember, serverless services are free or incredibly super cheap in low usage volumes. So even if your developers are picking away, running things in their own AWS accounts, the bills on these things will be zero or very close to it, because the usage billing often doesn't even kick in if you don't go over a certain threshold. So if for some reason you have a limitation where you can't give every developer their own AWS account, the next best step for that is then to create a separate AWS account for all developers to use together as their local testing environment, and then using the stage property that Serverless Framework gives you to deploy stacks that aren't going to step on other people working on similar things. So you can see serverless deploy -- stage Gareth means that this stack is going to deploy with the stage of Gareth, and I can now work without stepping on other people. It's not quite as nicely isolated as your own AWS account, but it can also get the job done if you are careful. And if you're wondering about all this AWS organizations, just create organizations all over the place. Well, there's a really great service within AWS itself called Organizations that you can create AWS accounts managed through a master AWS account. And where this is useful is if you do follow the idea of creating these AWS accounts per developer, and someone new joins your team, part of the onboarding could be to create them an AWS account in Organizations. You can even have some scripts that run at account creation stage to set some things up for them, set up permissions, give them access. And if somebody happens to leave, again, you just part of the process of them leaving is just to delete their AWS account from Organizations. Helps make that management a lot simpler. So here we come to the testing locally part that I've hinted at. And this is where I'm going to go through some of the topics about why I'm talking about a developer deploys into AWS and tests there and iterates in that way. And to set the scene, I want to also cover why it is that we currently, especially in traditional server-based architectures, why do we test locally? Where did this come from? And I mean, for me, I don't know about you guys, but every time I've joined a team, the first thing you're going to do is take your brand new machine that you provided, sit down with one of the other devs on the team, maybe for a couple of hours, maybe for a couple of days, it kind of varies, and then set up your local development environment. And this is what's done. This is what you do. That's just how things work, and you have a local development environment to start working on things. However, the reason why we have to have a local development environment is because in a world where our applications are living on these incredibly large clusters of machines, whether it's run by Kubernetes or just virtual machines, trying to replicate that, trying to have that level of replication of production becomes an incredibly expensive task to do. You can't give every developer on the team an exact replica of what production looks like when your architecture is, 20 virtual machines running different variations of Kubernetes and so on. So it becomes a necessity to have some way to replicate production at a smaller level that's cheaper on someone's local machine. However, this is really hard to do. It's actually really hard to accurately recreate your production environment on a local machine. It's something we've had to do in the past because we have no other choice, but it's still a very difficult thing to do. And this ultimately ends up leading to issues where I'm working on my local machine. I've built something which looks like it works great. I push this out into production and things start breaking and falling over. Works on my machine, but unfortunately in production it's broken. And now you're stuck not knowing whether it was the code you wrote or if there was some change between production and your local development environment that caused this issue because you didn't catch it locally. And because we've had to have local testing environments, we've kind of tried to make the most of it. We've added additional tooling on to help make the process feel a bit nicer. We've had some nice ways to sort of trace through the code we've been working on, debugging steps and so on. But ultimately, we're still in the situation where we have code that we're testing locally in an environment that's not very similar to production. And we're now in a situation in the serverless world where we are using these cloud services, and ultimately replicating cloud services locally actually becomes even harder to do because no longer is it just one CPU and another CPU. These are black box services that we're consuming through APIs. So some of the issues that we see when attempting to test locally is the replication of AWS services locally is very hard and time consuming. And I've been in the boat where I've spent lots of time trying to get local environments up and running to rather test locally before pushing stuff into AWS. And the problem with testing locally and building these large, complex local testing environments is that we are in a situation where one of the advantages that we've got with serverless development is we have this plethora of services available to us in AWS, for example. And if there's a really great service that we want to use that could completely revolutionize how we build this application, it can make it faster, cheaper, more efficient, whatever it is, it would be awesome to use. If, however, we are unable to replicate that service locally, that means that we are now stuck with two choices that we need to make. Either we decide that we need to just not use that service. We now need to essentially hamstring our application from using something that could make it better, and ultimately just discard that and continue to use only what's available to us because our local testing environment restricts us in that way. Or we decide, okay, this service is just too good to pass up. We need to use this. But that means our local testing environment no longer works because we can't write code that uses this new service, and then things break because we don't have it. So local testing no longer works. Tough decision to make. It's a tough position to be in. I've been there myself, and I know other folks who have as well. And it starts becoming tricky to work with. One step beyond that is to say, okay, never mind the services. I will use them remotely in AWS. Let's just mock things locally. Let's instead of consuming AWS services for testing, let's just use mocking to do this. And while that may seem like an improvement, the downside of this is that it becomes incredibly inaccurate over time because your engineering team now needs to write the mocks that returns the responses when talking to these remote services in AWS. And it becomes incredibly time-consuming now. Now you spend a lot of time writing all these mocks, maintaining them over time, especially when these services end up changing. And also to mention that Lambda functions, even if you get to the point where all you really want to do is run Lambda function code, run your code locally somehow, maybe in a container or some other situation, the Lambda functions do not operate the same way as your computer. It's not the same environment. And this has a big impact. If you take a look at some of the reasons why, Lambda functions run using Amazon Linux, not a Mac operating system. So there already you'll have differences in binaries, differences in libraries, and this crops up repeatedly when you're developing locally and then push it into the cloud. The Lambda function process gets killed. Once your Lambda function sends a return, that function ends execution immediately. And anything, especially in the JavaScript world, if you had code that was waiting its turn to execute asynchronously sitting in the JavaScript call stack, that code essentially gets killed. And this is a problem that I've seen happen repeatedly and often, mostly because folks are developing locally and don't see the issue and then deploy into AWS and then can't figure out what's gone wrong, why things aren't working the way they intend them to. Not to mention everything else that you're not seeing that comes with the cloud. Inter-service latencies, speaking to all these multiple services all the time. What do those latencies look like? On a local machine, they don't exist. The limits in the services. IAM permissions. There's so many different parts of building in the cloud that you will just not see when you're building things locally. So these can all cause potential problems. And this is why we end up advising folks to seriously consider looking at deploying and testing directly in the cloud from the get-go to save yourself a lot of pain and hassle trying to get up local testing environments, which can cause a lot of difficulty over time. But one of the issues that comes up with this is if you're trying to incorporate non-serverless type services into this, this is one of those really tough problems to solve. You know, if you have to include a relational database, which typically is not a serverless service, or you want to use Elasticsearch or something like that, these become really difficult to solve when you're trying to develop directly in the cloud. So there are a few ways you can look to help make this an easier way to work with. One of the things to now bear in mind is we've been looking at the sort of workflows, and you might have looked at these sort of staging and integration environments and gone, yeah, maybe I'll consider doing that. But if you are including non-serverless type services into your solution, this is where I would say it's almost an absolute requirement that you have some kind of staging environment at the very least prior to going to production. just to allow members of the team to find some way to integrate things and test against a local, a production replica, at least in a staging environment. And that can help this problem a lot as well. However, one step you can take beyond that for the individual developer developing is, why not consider that each developer has a copy of this resource deployed into their AWS account that they use for testing. Now, how this is useful is that, and this ultimately just depends on your budget, potentially, how far you're willing to go. You don't need to deploy an exact replica of the same size and complexity that you do in production, because you're not going to be managing huge load into these developer accounts. And if it's a relational database, you can spin up a very cheap relational database into an AWS account for about $10 a month. So that's just an additional cost of for each developer in your team, about $10 a month, getting a relational database up and running for them to test against inside their AWS account. The other way to do this, the next best way to do this, is to provide a shared deployment for the entire team to use as a whole. And why this isn't as ideal is because at this point now you're introducing communication complexities. If changes need to be made to this shared deployment, this is going to require your team to communicate together and work together on these changes so that everybody fully understands them. But ultimately, you can connect resources between AWS accounts and share, for example, a relational database from one AWS account to another. And this can help you in that way have these non-serverless services available for developers while they're still developing and testing in the cloud as well. So that becomes pretty useful. And the last option I mentioned is mocking. This is probably not the best option to use here because it has all the same problems as I've mentioned before with mocking, maintaining them, taking time to build them. It's very time consuming. But if you do want to find some way to kind of eliminate the shared deployment and allow developers to use things locally, mocking is potentially an option for that, so that you can rather use a mocked version of these non-serverless services. Okay, so we're going to take a look at managing shared and production environments, and I know we're kind of going to start running up against time, so I'm going to try and do this as quickly as I possibly can, and then we can maybe do a last flurry of questions. But when you've got your application built and you want to deploy this into your staging environments or into production, how do you manage these things? And one of the things that we're going to look at through this is, for example, how do you manage access to the AWS accounts for production, for staging, and so on? And the AWS recommendation is that you have one AWS account for your integration environments, and all the different environments that you have. And I saw the question about different environments. So ultimately, what a different environment is if you deploy with a different stage. So as a developer, I'm going to deploy to my stage, which will be my local development environment. When I deploy into an integration environment, that's going to be to -- stage staging maybe, or -- stage dev. So this is the development environment. And each of those you want to have in different AWS accounts potentially. To just for separation and for security reasons, many other reasons that you want to have all these things in separate AWS accounts. So your staging and production environments should be in separate AWS accounts as well. But we need to manage that. How do you manage those connections? And ultimately, these different environments also will need different configuration data across these multiple environments. So how do I make sure that I get the right connection strings, for example, or I use sandbox connection data for my dev environment, but I need the production values for my production environment without having to mess around with your configuration every time you deploy to a different environment. We also need to find a way to look at our production environment and assess the performance characteristics to optimize it, and also to keep an eye on errors and potentially be alerted to them. And this is where I'm going to take a look at a tool that we built internally at Serverless called the Serverless Dashboard. These are problems that kind of plague almost all serverless applications, and they're kind of tricky problems to solve. And ultimately, we ended up building a tool that's available free to use for anybody to try out and look at, is the dashboard. If you go to serverless.com/dashboard and take a look. But let's go through a few steps and take a look at what this looks like when you're building your application. And to start us off, I'm looking at a feature here called providers. Now, what providers is a feature we've created in the dashboard to allow you to manage multiple AWS accounts and multiple environments together, and for you to set up a way for you to deploy to these environments and ensure that you're always going to be using the right connections to the right AWS accounts for them. So in this example, you can see I've got 4 different connections here to what might be different AWS accounts, 2 dev ones and 2 production ones. And let's see how we can set these up. One of those was a default. And if I look at here, for example, here's a specific service with a stage called dev. And here you can see this has inherited the default provider that we saw on the previous screen. Any stage that hasn't got a specific provider allocated to it uses the default, so we'll always be able to deploy into this dev environment. However, for my production stage, I want to deploy into production. So here's the production stage, and I've clicked, in this case, the big orange Add Provider button and overridden the default provider with the production provider. So in this situation, I can now be guaranteed that if we make a deployment to --stage prod, the deployment will always occur using this specific provider to that specific AWS account. And this guarantees that because I'm controlling this centrally. And if I'm not spreading out access credentials to these AWS accounts in other ways, I now have, this is the only way that things can be deployed. Very useful to help manage how I deploy things into my various environments. Another part of that is often I have configuration data that I want to use. I need a way to set up configuration data, connection strings, config values, whatever it might be for specific environments. And the dashboard provides me a feature called parameters. And parameters is a way at the service level here. So I have a service here called Orders Gateway. And at the service level, I can set up a parameter. And here I've got 2 of them, config value 1 and 2, with specific values that are hidden because they're encrypted. And I want, at all my services, my dev stage, my prod stage, any stage that I deploy to an environment I deploy to, these config values are available to them. And I can access these values in my serverless, the YAML file, so I can access the values at deployment time. When I run serverless deploy, $param is replaced with the actual value for these specific parameters. However, these might change depending on the specific environment. So here, for example, I'm on my dev stage for Orders Gateway. You can see I've got config value 1 and 2 are automatically inherited here. And I've got the option to override this with a dev specific value that I want for my dev stage. Or I can even add a parameter that's only going to be available to the dev stage as well. So I kind of have some nice flexibility there in managing what configuration values are available to my service as a whole for defaults, and then override them at the specific stage level to help restrict those and maintain it. And I've got a quick little video that I wanted to share at what that looks at some of the other options that the things we need to concern ourselves with when building a serverless application. And what I've done is I've got an example here of an application, and I'm just going to take that back to the beginning quickly. I'm just looking at the dashboard here, and I want to go take a look at my dev instance for my Orders Gateway that is deployed here. So if I go through and I just click through to look at that, and I'm going to get to an overview screen, which is going to show me some metrics for my deployed application, my deployed service. I can see I've got some function invocations and some errors. So let's go take a look at these errors by clicking through from the chart like that. And now I've gotten a list of these are specific Lambda invocations that errored out in that time frame that I clicked on. So I can immediately see what these are. And I want to go look in more detail at one of them. So let's just click through to see more detail on these specific errors. And I can go through this and see a lot of information here that can help me potentially solve this, including information about the stack trace. So I've got a message here showing me that my handler.py errored out on line 22, as well as the full log available to me to go take a look at to help me debug this error that's happening here for me to look at. But I can also look at some more performance metrics. I can go directly to the functions tab for the specific stage and see some more details about memory usage and duration, for example. Here, for example, I might decrease the amount of memory used and save myself some money, but then keep an eye on duration to make sure that doesn't affect the latency of my Lambda functions. Maybe I make a deployment and I can come to this durations graph to see how my deployment has affected the duration of my Lambda function. Maybe I've increased the latency, which is something to avoid. But ultimately, I don't want to sit around looking at the dashboard all the time to see if an error has cropped up. So I can add, for example, an alert. You can do that on Slack, with email, SNS, and so on. Receive error rates. Choose a specific channel in your Slack workspace. And instead of having to sit on the dashboard looking at things to see if errors come up, you can add an alert so that you can get notified about issues that might crop up on your application in production. This is a great way just to keep getting alerted and make sure that nothing's going wrong for your users without your knowledge. Yeah. So I'm going to rush to the summary. We recommend developing and testing directly in the cloud. Use AWS organizations to help manage your multiple AWS accounts. Local testing environments are really hard to get right and maintain over time. So bear that in mind if you ever decide to go down that road. You do have an alternative. Developing and testing in the cloud is available and really good. There are tools that exist as well to help you manage multiple shared environments and deploying into them and managing configuration data. And monitoring production environments is a critical part of a production application. And with that, I'm going to say thank you very much. I think we might be able to do some final questions. I'm not sure how we're looking on time. But if you did ask a question that wasn't answered, feel free to contact me. My email address is gareth@serverless.com. We also have our fantastic community Slack. So if you do find you want some more takes on your issues that you might be dealing with building a serverless application, go to serverless.com/Slack. There are thousands of people there that might have the same issue you're dealing with and know how to help you out. Yeah, and I'll hand it over to Richard now.
Yeah, and we're over here about 6 minutes. I don't know if you wanted to take just a couple minutes to still answer some questions or just rely on people.
Hey, let's do it.
Awesome. First question from Patrick. What are we referring to when we say different environments? Is that done via different AWS accounts, VPC isolation?
Yeah, so I did kind of answer that question as we were going as well. Just to reiterate, different environments means using SLS stage to potentially deploy to different environments, and then ultimately into different AWS accounts. And Serverless Dashboard can help you manage those multiple environments as well centrally. So that makes life a little bit easier. Yeah.
Awesome. And then the second question from Hector: serverless is recommended for initial devs, or is more reliably for senior ones?
Interesting question. So my take on that is, if you're brand spanking new into building applications for the web, you may want to focus on learning about writing code and so on as a new developer. Cloud infrastructure is something that you can get into over time. And once you're confident that you kind of have gotten sort of the code stuff, you've learned more about how to deal with code. Getting into the cloud, actually, I found getting into the cloud using serverless was the easiest way to do it, because ultimately you've got the serverless framework documentation, and you can go looking through the list of events supported by the framework, and you can see, oh, what is this thing called SNS? Go do a bit more research. Now you've learned about a new AWS service. So it's a combination of both. Focus first, if you're a new developer, on learning how to code, and then look at using the serverless framework to help inform your choices in what to learn about the cloud and how you can use all these services in the cloud potentially when you're building your application. Really cool stuff.
And one more from Ryan. Can you set up alerts or for any error ever, or can it only do new error types like the checkbox said? All
right, so maybe the description on the checkbox is a little misleading. I can go back to the product team with that. But what that means really is that new error type refers to essentially over a 48-hour period. Because the last thing we want to do is you get an error from one of your users, and you have thousands of users, and they're all hitting the same error, and you get 1,000 notifications that each of these people have had the same error. So ultimately, we see this as a new error type. We notify you one time, and when it comes up again within space of 48 hours, we're not going to alert you on that, because otherwise you just get spammed out of existence. So after that 48 hours have passed, if that same error type comes up again, then we'll notify you again on it. New error types just means we have not seen this error before, so we will notify. And if we see it again in 48 hours, then we just don't until that period passes. So that's usually what that means.
We have two more questions just coming in. Hector says, could you share to us some ideas to mock up the services, or what are you used to?
Well, Like I said before, mocking is, I think, potentially a last resort that you should consider, just because of that management overhead over time. But if you absolutely have to go down that route, there are a couple of tools that make it a little bit a little easier to do. One of the tools that I've used in the past, I used to set up my mocks via sort of a unit testing framework, and using a tool like AWS SDK Mock. It's an NPM module. Becomes pretty useful for that. Makes it a bit easier to communicate with the AWS SDK and mock out the responses you'd get from those services. But yeah, again, over time, you're gonna end up finding that writing and maintaining these mockups end up being very time consuming and costly. But yeah, that's the tool I've used in the past.
Last question: does a serverless dashboard stores data, logs, metrics, etc., at some server in your serverless infrastructure, or does it fetch a data from associated AWS accounts on the fly?
Nice, insightful question. So interestingly, what it's going to be a bit too detailed to go into the full discussion of this, but ultimately the CloudWatch logs that you see printed on the screen that I had there, we don't store that. That's not actually stored on our side at all. When you view that specific invocation, if I had scrolled down fast enough, you would have seen the CloudWatch log taking a second or two to load extra, because we use the AWS API to then retrieve those logs to display to you on the screen, so that you get to see it then. We don't store that log generally. What does happen though is that at the execution time of your Lambda function, we do use CloudWatch to push data asynchronously, the metrics data that we use for everything you saw in the monitoring portion. And this is useful because it keeps the latency of the monitoring service to an absolute minimum. There's no added latency. We don't make any HTTP calls, so it doesn't add time for your Lambda function to execute, which is pretty cool. But it means we can retrieve that data later through a CloudWatch subscription. Only the stuff that we've put there. You can see if you do use the dashboard and you look at your CloudWatch subscriptions, you can see we put a filter in place to only retrieve the stuff that we put there in the first place. And that's what's used for your metrics. And those logs are pulled in later when you view them.